So in this lecture we are discussing about one of the very most important desulfurization or the sweetening process used in the commercial industries, in the natural gas industry, is the Alkanolamines processes. That is one of the very famous process used for the desulfurization of the natural gas. So in the alkanolamine, it is basically the chemical absorption process. It means there are some reactions involved in this one. It's not a physical absorption process. It is the most widely used solvent for the removal of acid gases, that is a H2S and CO2. This process was started or patented in 1930s, so you can say that it's one of the very old process in the field of sweetening. So due to their reactivity and the low cost availability, alkanolamines have achieved the prominent position in the gas industry. That is a very basic reason, because ultimately everything is always preferred in terms of the economics, and also it is a very good activity towards the acid gases, especially the monoethanolamines and diethanolamines. So they offer good reactivity at a very low cost and a good flexibility in design and operations. So these are the few advantages. Because of that, people are very much interested in the alkanolamine sweetening process. So there are few types of the solvents available in the field of alkanolamines. For example, one is the monoethanolamines, second is the diethanolamines, triethanolamines, diglycolamine and diisopropanolamine, and methyl diethanolamine. So these are the few famous, or you can say the few very common type of the alkanolamines used in this sweetening process. So these are the diagrams. Monoethanolamines. So you can see the ethanol and how this NH2 group is attached here. So amines group is attached with that one, monoethanol. Here the diethanol is amine is attached with the amines, and this is a triethanolamines is attached. This is diglycolamines and diisopropanolamine, methyl diethanolamines. So these are the structures of the alkanolamines, and these are the some basic properties of all these amines. You can see here their chemical formula is given, their name is given here, their molecular weight. So mono is the lowest molecular weight, and so on. You can see how it is increasing. So this molecular weight is necessary because we know that number of moles is nothing but the amount upon molecular weight. So amount is calculated by this into molecular weight. So anyhow, this molecular weight is one of the very important thing for the calculation of amount. So that's why molecular weight is required here. The second property that is important is the vapor pressure at 100 degree Fahrenheit mmHg. Means more vapor pressure. This one is the more vapor pressure. Obviously, it means that it have a less boiling point. So more vapor pressure means more vapor pressure implies that more loss. Simple definition. So that is a problem with the higher vapor pressure, but still we are using the amines, monoethanolamines, because of the few reasons. For example, if we see the relative capacity percentage, if we assume that this 100% monoethanolamines, with respect to the monoethanolamines, these are the performance of the other amines. It's hardly 58, 41, 58, 46 and 51% relative capacity. So if you see about here, the monoethanolamines offer very good as compared to the other amines. So these properties are basically gives us so many informations that is useful for the designing of the these towers, amines towers. Now come to the monoethanol, the number one, the first one, their merits, because very popular one. So this have the highest reactivity in all the amines, and therefore the highest acid gas removal capacity. That's why it's the highest. We have taken the 100%. With reference to that, we have calculated all the other, and that are very less one. These are the very less one as compared to the monoethanolamines. So monoethanolamines have the highest capacity. The second is have the lower molecular weight among all the amines. Therefore, it offers the highest removal capacity on the unit weight or the unit volume basis. I have told you that this molecular weight is related with the amounts, which implies lower solution circulation rates in the sweetening plant. So in this way, we have a low amount. The next third one is it chemically stable. Minimum solution degradation is basically possible in this MEA. The reaction rate of H2S with Me is greater than the CO2, and the process, however, is considered to be almost non-selective in the removal capacity of H2S and CO2. Although they have a very good rate towards the H2S, but almost CO2 and H2S both are recovered and both are removed with the help of this MEA process. MEA is able to remove the acid gases up to the pipeline specification, and even the beyond, means even lesser than that one. So that's why this MEA is a very good one. But there are few disadvantages and demerits of the MEA. MEA suffer from relatively high solution losses, primarily due to the two reasons. This is one of the very big disadvantage: high solution losses. It has a relatively high vapor pressures that causes the greater evaporation losses, and the second is it reacts irreversibly with carbonyl sulfide and carbon disulfides. If these two materials are present in the natural gas, what happens? They will react with the MEA, that is the monoethanolamines, and there will be the loss of that one, because they are the irreversible process. Means now we cannot regenerate again the MEA from the carbonyl sulfide reactions and from the carbon disulfide reaction. So that's why it is simply the loss. It is considered the loss of the MEA solution. High evaporation losses put a limitations on the operating temperature, which must be kept at the. So we have to, if suppose we want to maintain the low losses, so we have to maintain the low temperature. Whereas the reaction leading to build up the solid necessitate efficient filtration schemes. So these solid materials sometimes after the reactions, these carbonyl sulfide and carbon disulfides and some other materials, they are basically forming the solid structure. They have to be require the efficient filtering scheme in the MEA. If you discuss about the second, that is the diethanolamines, it is very much similar to the MEA, except it is not as reactive as the MEA. Number one, H2S removal to pipeline specification may cause problems in some cases. So you cannot go up to the pipeline specification. Sometimes you have to tolerate some more concentration of H2S in that process. Its reaction with carbonyl sulfide and carbon disulfide are slower and led to different products, so filtration problem are less. So here the problem with the carbonyl sulfide and carbon disulfide are less as compared to the MEA, and its vapor pressure is lower, therefore evaporation losses is less. Thus DEA can be advantageous to use in some cases. So that is a few advantages of the DEA. Come to the TEA, tertiary and diisopropanol and MDEA. They almost have totally replaced the MEA and DEA. Both has been replaced by tertiary ethanolamines, primarily because it has a lesser activity and problems as compared to the other, basically the MEA and DEA encountered in the sweetening gas up to the pipeline specifications. DIPA is also able to treat the gas up to the pipeline specification and is used in the sulfonol process by the Shell and ADPI IP process. So DIPA is also used in some industries. MDEA has received the renewed attention because it has a fairly good selectivity for the H2S and CO2 and can be retained selectivity towards the H2S and CO2 can be retained in the gas, and it offers some energy saving in the regeneration steps. So MDEA, however, may not be commercially competitive with the other amine process. In short, if I say that T is a very much popular, DIPs, people are using the DIPA also. So we can say that these are the few comparison of these different type of the solvents available for the desulfurization. So that's all about the comparison. Thank you very much.